Right now, as you lie still in the comfort of your bed, you are hurtling through space at over 1 million miles per hour. Your body registers no sensation of this movement. No wind rushes past your face. No acceleration pushes you backward. The water in the glass beside you sits perfectly level, undisturbed. You feel completely, utterly stationary. This is one of the most profound illusions your senses have ever produced. Every cell in your body, every atom of your being is engaged in a cosmic ballet of velocities so extreme they defy human comprehension. Yet the sensation of motion is entirely absent. The disconnect between reality and perception could not be more complete. Understanding why this happens requires unpacking multiple layers of motion, each one stacking on top of the others like Russian dolls of velocity. You are not moving at just one speed through space. You are moving at many speeds simultaneously, in different directions on different scales. The Earth rotates on its axis. The Earth orbits the Sun. The Sun orbits the center of the Milky Way galaxy. The Milky Way itself moves through space relative to other galaxies. And underneath all of this, the very fabric of space itself expands, carrying everything with it. When you add these velocities together, using proper geometric calculations, the numbers become staggering. The sensation of stillness you feel right now is a carefully constructed fiction, a trick of physics that allows you to function in a universe that would otherwise be incomprehensible. Let's start with the smallest scale, the one closest to your immediate experience. The Earth spins on its axis once every 24 hours, completing a full rotation that produces our cycle of day and night. This rotation means that if you are standing at the equator, you are moving eastward at roughly 1,000 miles per hour. That is faster than the speed of sound. You are breaking the sound barrier just by standing still. The farther you are from the equator, the slower your rotational speed, because you are tracing a smaller circle around Earth's axis. At the poles, your rotational speed approaches zero, but for most inhabited places on Earth, you are spinning at hundreds of miles per hour. The atmosphere spins with you, which is why you feel no wind from this rotation. The ground beneath you spins with you. Everything in your frame of reference shares this motion, so relative to everything around you, you are motionless. This is the first principle of why you feel nothing. But Earth's rotation is just the beginning. The Earth orbits the Sun at a much greater velocity. Our planet traces an elliptical path around our star, completing one full orbit every 365.25 days. The distance Earth travels during one orbit is roughly 584 million miles. Divide that distance by the number of hours in a year, and you get Earth's orbital speed around the Sun, which is about 67,000 miles per hour. Think about that number for a moment. Right now, you are moving through space at 67,000 miles per hour relative to the Sun. That is more than 80 times faster than a speeding bullet. Yet you feel absolutely nothing. No sensation of acceleration, no cosmic wind, no indication whatsoever that you are screaming through the void at speeds that would vaporize any spacecraft we have ever built if it tried to plow through an atmosphere at that velocity. Here's where the mathematics of motion start to reveal something profound. Speed is not absolute. Speed is always relative to something else. When we say the Earth moves at 67,000 miles per hour around the Sun, we mean relative to the Sun. When we say you are spinning at 1,000 miles per hour, we mean relative to Earth's axis. But what happens when we ask how fast the Sun itself is moving? The answer opens up an entirely new scale of velocity. The Sun, along with the Earth and all the other planets, orbits the center of the Milky Way galaxy. This orbit is not a simple circle. It is a complex path influenced by the gravitational pull of billions of stars, the dark matter halo that surrounds our galaxy, and the overall structure of the galactic disk. The Sun is located roughly 26,000 light-years from the galactic center, embedded in one of the spiral arms. At this distance, the Sun's orbital velocity around the galactic center is approximately 500,000 miles per hour. That number is almost incomprehensible. 500,000 miles per hour. You are moving at 500,000 miles per hour right now, just from the Sun's orbital motion around the galaxy. But we are not finished, not even close. The Milky Way galaxy itself is not stationary. Galaxies move through space relative to one another, pulled by gravity, shaped by the expansion of space, influenced by large-scale structures that span hundreds of millions of light-years. The Milky Way is part of a small group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller galaxies. The Local Group itself is moving through space as part of the larger cosmic flow. Astronomers have measured this motion by examining the cosmic microwave background, the afterglow of the Big Bang that fills all of space. The cosmic microwave background appears slightly warmer in one direction of the sky and slightly cooler in the opposite direction. This temperature difference is caused by the Doppler effect. As we move toward the warmer region, the light waves compress, increasing their frequency and temperature. As we move away from the cooler region, the light waves stretch, decreasing their frequency and temperature. By measuring this temperature difference precisely, scientists have determined that the local group is moving at about 390 miles per second relative to the cosmic microwave background. That is roughly 1.4 million miles per hour. 1.4 million miles per hour. This is the combined motion of everything we have discussed so far. Earth's rotation, Earth's orbit around the Sun, the Sun's orbit around the galaxy, and the Milky Way's motion through space. When you add these velocities together as vectors, accounting for the different directions of each motion, you arrive at this staggering number. You are moving at 1.4 million miles per hour through the universe right now. And you feel nothing. Not a tremor, not a whisper of wind, not the slightest hint of acceleration. The question is not just why you feel nothing. The question is how it is even possible for motion of this magnitude to exist without producing any sensation whatsoever. The answer lies in one of the most elegant and counterintuitive principles in all of physics. You cannot feel constant velocity. You can only feel acceleration. This distinction is absolutely crucial to understanding why cosmic motion is imperceptible. Acceleration is a change in velocity, either in magnitude or direction. When a car speeds up, you feel pressed back into your seat. When a car slows down, you feel pulled forward. When a car turns, you feel pushed to the side. These sensations are caused by your body's resistance to changes in motion. Your inner ear contains fluid and tiny hair cells that detect acceleration. Your muscles and joints register forces that arise from changes in velocity. But when velocity is constant, when there is no change in speed or direction, there is no force acting on your body. There is nothing for your senses to detect. This principle was first clearly articulated by Galileo Galilei in the early 17th century, though he did not have the mathematical framework to express it with full precision. Galileo realized that the motion of a ship sailing smoothly on calm water is imperceptible to passengers below deck. If the ship moves at a constant velocity, passengers cannot tell whether the ship is moving or stationary without looking outside. Objects fall straight down. Water pours normally. Everything behaves exactly as it would if the ship were at rest. This observation was revolutionary because it challenged the intuitive notion that rest and motion are fundamentally different states. Galileo understood that rest and constant motion are physically indistinguishable. This insight laid the groundwork for what would eventually become Einstein's theory of relativity. The principle is called Galilean relativity, and it states that the laws of physics are the same in all inertial reference frames, which are reference frames moving at constant velocity relative to one another. Newton formalized this understanding with his first law of motion, often called the law of inertia. An object at rest stays at rest, and an object in motion stays in motion at constant velocity unless acted upon by an external force. This law implies that there is no absolute state of rest or absolute state of motion. You can only measure motion relative to something else. From the perspective of someone sitting on Earth, the ground is at rest. From the perspective of someone watching from the sun, the Earth is moving at 67,000 miles per hour. Both perspectives are equally valid. Neither is more correct than the other. This is not a limitation of our measurement tools. This is a fundamental feature of how space and motion work. The Earth's rotation, its orbit around the Sun, the Sun's orbit around the galaxy, and the galaxy's motion through space all happen at essentially constant velocities over timescales that matter to human perception. Yes, there are tiny accelerations. The Earth's orbit around the Sun is not perfectly constant. It involves centripetal acceleration toward the Sun to maintain the curved path. But this acceleration is incredibly small compared to the velocities involved. The centripetal acceleration from Earth's orbit around the Sun is about 6 millimeters per second squared. Compare that to the acceleration you feel from gravity, which is 9.8 meters per second squared. Earth's orbital acceleration is less than 1,000% of the acceleration of gravity. Your body cannot detect such a tiny change. The same principle applies to all the other cosmic motions we have discussed. The accelerations involved are real but minuscule compared to the sensations we are accustomed to feeling. There is another layer to this. Everything around you shares your motion. The atmosphere moves with the Earth as it rotates and orbits. The oceans move with the Earth. The ground beneath you moves with the Earth. Your body, the air in your lungs, the neurons firing in your brain, all of it moves together at the same velocity. Because everything in your immediate environment shares the same motion, there is no relative motion between you and your surroundings. This is why the air does not blast past you at 1,000 miles per hour from the Earth's rotation. The air is rotating with you. This is why water does not slosh out of a glass as the Earth orbits the Sun at 67,000 miles per hour. The water is orbiting with you. Motion only becomes perceptible when there is relative motion between you and something else. And on the scale of cosmic velocities, everything nearby is moving together as a cohesive unit. Here's where it gets strange. The expansion of space adds yet another layer of motion, one that operates on a completely different principle. The expansion of space is not motion through space. It is the expansion of space itself. This distinction might seem subtle, but it is absolutely fundamental. When we say the universe is expanding, we do not mean that galaxies are flying away from each other through a pre-existing void. We mean that the distances between galaxies are increasing because the fabric of space itself is stretching. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they are traveling across the rubber, but because the rubber itself is expanding between them. This is how cosmic expansion works. Space itself grows, and everything embedded in space gets carried along for the ride. The rate of this expansion is described by the Hubble constant, named after Edwin Hubble, who first measured the expansion of the universe in 1929. The current best measurements place the Hubble constant at about 70 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. What this means is that for every 3.26 million light-years of distance, space is expanding at a rate that carries objects apart at 70 kilometers per second. For nearby galaxies, this expansion is negligible, overwhelmed by local gravitational attractions. But for distant galaxies billions of light-years away, the expansion of space dominates, causing them to recede from us at enormous speeds. Some galaxies are receding faster than the speed of light, not because they are moving through space faster than light, but because the space between us and them is expanding rapidly. This does not violate relativity because nothing is moving through space faster than light. The space itself is growing. Does the expansion of space affect your body? Does it stretch the atoms in your cells, increase the distance between your molecules, pull you apart at the seams? It does not. The expansion of space only affects regions where gravitational binding is weak or absent. Your body is held together by electromagnetic forces between atoms, which are vastly stronger than the cosmological expansion on small scales. The Earth is held together by gravity. The solar system is held together by the sun's gravity. The Milky Way galaxy is held together by its own gravity and the gravity of its dark matter halo. Even the local group of galaxies is gravitationally bound. The expansion of space only becomes significant on scales larger than about 100 million light-years, where the density of matter drops low enough that gravity cannot counteract the expansion. On human scales, on planetary scales, even on galactic scales, the expansion of space is completely negligible. You are not being stretched by the expansion of the universe. The atoms in your body maintain their size. The distances between planets remain constant. The Milky Way does not grow. Expansion only wins the tug-of-war with gravity on the largest cosmic scales. Think about the layers we have unpacked. You sit still in your bed, feeling nothing, but you are spinning at 1,000 miles per hour from Earth's rotation. You are orbiting the Sun at 67,000 miles per hour. The Sun is orbiting the Milky Way at 500,000 miles per hour. The Milky Way is moving through space at roughly 1.4 million miles per hour relative to the cosmic microwave background. And beneath all of this, space itself is expanding, though not fast enough to affect you directly. Each of these motions is real. Each can be measured. Each has consequences that ripple through the cosmos. Yet the combined effect on your senses is precisely zero. This is not a failure of your perception. This is a deep truth about the nature of motion and reference frames. Constant velocity is indistinguishable from rest. Only changes in velocity produce forces that you can feel. The history of understanding these motions spans centuries and represents one of humanity's greatest intellectual achievements. Ancient astronomers believed the Earth was stationary at the center of the universe, with the sun, moon, planets, and stars revolving around it. This geocentric model, perfected by Claudius Ptolemy in the 2nd century, worked reasonably well for predicting the positions of celestial objects. It matched everyday experience. The ground felt solid and unmoving. The heavens appeared to turn above. Why would anyone think otherwise? The idea that the Earth moved seemed absurd. If the Earth moved, surely we would feel it. Birds would be left behind. Objects thrown into the air would land far from where they were thrown. The fact that none of these things happened seemed like ironclad proof that the Earth was stationary. Nicholas Copernicus challenged this view in 1543 with the publication of his book On the Revolutions of the Heavenly Spheres. Copernicus proposed that the Earth rotates on its axis and orbits the Sun, along with the other planets. This heliocentric model simplified many of the complex motions observed in the night sky. Retrograde motion of planets, where planets appear to move backward against the background of stars, became a natural consequence of the Earth overtaking slower-moving outer planets in its orbit. But Copernicus faced a major objection. If the Earth moves, why do we not feel it? Copernicus could not provide a satisfactory physical explanation. He understood the geometry of planetary motion, but the underlying physics remained elusive. The argument that we do not feel Earth's motion because everything moves together was philosophically unsatisfying to many scholars of the time. They wanted a mechanistic explanation grounded in the principles of motion. That explanation came from Galileo and Newton. Galileo's observations with his telescope provided strong evidence for the Copernican model. He saw moons orbiting Jupiter, which demonstrated that not everything revolves around the Earth. He observed phases of Venus, which could only occur if Venus orbits the Sun. He saw mountains on the Moon and spots on the Sun, which challenged the Aristotelian notion that celestial bodies were perfect and unchanging. But perhaps Galileo's most important contribution was his principle of relativity, which explained why we feel no motion despite the Earth's rotation and orbit. Newton's laws of motion, published in 1687 in his Principia Mathematica, provided the mathematical framework to understand inertia, force, and acceleration. Newton showed that motion does not require a force, only changes in motion require forces. An object in motion will continue moving at constant velocity forever unless something pushes or pulls on it. This explained why the Earth's motion through space does not produce any sensation. Measuring the Sun's motion around the galaxy came much later in the 20th century, as astronomers began to map the structure and rotation of the Milky Way. In 1927, Dutch astronomer Jan Oort analyzed the motions of nearby stars and determined that the Sun is moving around the galactic center at approximately 220 kilometers per second, or about 490,000 miles per hour. This measurement has been refined over the decades using radio observations of gas clouds, optical observations of stars, and infrared surveys that peer through dust to map the galactic structure. The latest measurements place the Sun's orbital speed at around 230 kilometers per second, slightly higher than Oort's original estimate. At this speed, the Sun takes roughly 230 million years to complete one orbit around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs had not yet appeared on Earth. The discovery of the Milky Way's motion through space relative to the cosmic microwave background came in the 1970s and 1980s. The cosmic microwave background was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were testing a sensitive radio antenna and kept detecting a persistent noise that would not go away. They eventually realized that the noise was not coming from their equipment or from Earth. It was coming from space itself, from every direction. This uniform glow of microwave radiation is the cooled remnant of the Big Bang, emitted when the universe was only 380,000 years old and finally became transparent to light. The temperature of this radiation is remarkably uniform, about 2.7 Kelvin, but there is a slight variation, a dipole pattern where one side of the sky is slightly warmer and the opposite side is slightly cooler. This dipole was measured precisely by the COBE satellite in the early 1990s. The temperature difference is tiny, only about 3 millikelvin, but it reveals our motion through space. The Milky Way is moving at about 630 kilometers per second relative to the cosmic microwave background rest frame, carrying us in the direction of the constellation Hydra. What drives this motion? Why is the Milky Way moving in this particular direction at this particular speed? The answer involves large-scale structures in the universe that were not fully understood until the late 20th century. Galaxies are not distributed randomly through space. They cluster together in groups, clusters, and superclusters, forming a cosmic web of filaments and walls surrounding vast voids. The Milky Way is part of the local group, which is being pulled toward a massive concentration of galaxies in the direction of the constellations Centaurus and Hydra. This concentration is called the Great Attractor, and it was identified in the 1980s through studies of galaxy motions. The Great Attractor is not a single object, but a region of space containing tens of thousands of galaxies, whose combined gravitational pull influences the motion of galaxies across hundreds of millions of light years. But the story does not end with the Great Attractor. In 2005, astronomers discovered an even larger structure affecting the motion of the local group and the Great Attractor itself. This structure is called the Shapley Supercluster, and it lies beyond the Great Attractor, containing tens of thousands of galaxies concentrated in a volume roughly 500 million light-years away. The Shapley Supercluster is one of the most massive structures in the observable universe, and its gravitational pull extends across truly staggering distances. The combined influence of the Great Attractor and the Shapley Supercluster accounts for much of the Milky Way's motion through space. Gravity from these massive structures has been pulling on our galaxy for billions of years, accelerating it to its current velocity of over 1 million miles per hour. Here's the uncomfortable part. We are not just moving toward these structures, we are falling toward them. The motion of the Milky Way through space is not leftover momentum from the Big Bang. It is ongoing gravitational infall toward regions of higher matter density. This fall has been happening for billions of years, ever since the early universe developed slight density variations that grew under their own gravity. Regions that were slightly denser than average attracted more matter, becoming even denser. Regions that were slightly less dense than average lost matter, becoming voids. Over billions of years, this process amplified the tiny density fluctuations present in the early universe into the large-scale structure we see today. The Milky Way formed in a region of relatively high density and has been falling toward even denser regions ever since. This fall will continue for billions of years into the future, eventually leading to a merger between the local group and other nearby groups of galaxies. The Great Attractor and the Shapley Supercluster are not destinations we will reach on human timescales. They are gravitational beacons guiding the long-term evolution of structure in this corner of the universe. Calculate what happens next. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, the largest member of the local group. This collision is inevitable because the two galaxies are approaching each other at about 110 kilometers per second, fast enough to close the current gap of roughly 2.5 million light-years in a few billion years. The collision will not be a sudden impact. Galaxies are mostly empty space, so the stars in the two galaxies will pass through each other without directly colliding. But the gravitational interactions will be catastrophic for the overall structure of both galaxies. Stars will be flung into new orbits. The spiral arms will be disrupted. Gas clouds will collide, triggering intense bursts of star formation. Over the course of a few billion years, the two galaxies will merge into a single, larger elliptical galaxy, sometimes referred to as Milky Way. The Sun and Solar System will likely survive this merger, though our position in the galaxy will change. We might be flung into the outer halo, far from the galactic center. Or we might be pulled closer to the center. The outcome for individual stars is unpredictable, determined by the chaotic gravitational interactions during the merger. But even this merger is just one step in a longer process. After the Milky Way and Andromeda merge, the combined galaxy will continue falling toward the larger structures in our cosmic neighborhood. The merged system will eventually interact with other galaxies in the region, leading to further mergers and rearrangements. Over tens of billions of years, the local group will likely merge with other nearby groups, forming a single massive galaxy cluster. This process is driven by gravity, which is the dominant force shaping the universe on large scales. Gravity never rests. It pulls constantly, inexorably, reshaping the cosmos over timescales that dwarf human history. The motion of the Milky Way through space is part of this larger story, a chapter in the ongoing gravitational evolution of the universe. Understanding our motion through space requires understanding our position within this cosmic hierarchy. We live on a planet orbiting an ordinary star in the outer regions of a spiral galaxy. The Milky Way contains roughly 200 billion stars, along with vast amounts of dark matter and interstellar gas. Our solar system is located about 26,000 light-years from the galactic center, in the Orion Arm, a minor spiral arm between the larger Perseus and Sagittarius arms. This position is neither central nor peripheral. We are not at the heart of the galaxy, where stars are densely packed and supermassive black holes lurk. Nor are we in the outermost halo, where stars are sparse and lonely. We occupy a middle ground, a relatively calm region where stars are spaced far enough apart that close encounters are rare. This location has consequences. The density of stars in our neighborhood is low enough that the night sky is dark, allowing us to see distant galaxies and the faint glow of the cosmic microwave background. If we lived closer to the galactic center, the sky would be blazing with starlight, making it difficult to observe the larger universe. The rate of supernovae would be higher near the galactic center, increasing the radiation environment and potentially making it harder for complex life to develop. Our position also means that our view of the universe is shaped by the Milky Way's structure. The disk of the galaxy appears as the Milky Way band across the night sky, a river of light composed of billions of stars too distant to resolve individually. Dust in the galactic plane obscures our view in certain directions, particularly toward the galactic center, which is why many astronomical surveys focus on regions above and below the plane. The Milky Way's motion through space affects what we can observe, because we are moving at 630 kilometers per second relative to the cosmic microwave background. That motion imprints a dipole pattern on the cosmic microwave background temperature map. This dipole is the largest signal in the cosmic microwave background, far larger than the tiny fluctuations that reveal the density structure of the early universe. To study those tiny fluctuations, astronomers must first subtract the dipole caused by our motion. This correction is straightforward, but it reminds us that our observations are always made from a moving platform. We cannot observe the universe from a position of absolute rest, because no such position exists. Every measurement we make is influenced by our motion through space, and we must account for that motion to understand what we are seeing. Here's the problem. Our motion through space creates a puzzle that cosmologists are still working to fully understand. The velocity of 630 kilometers per second measured relative to the cosmic microwave background is larger than what standard cosmological models predict for a typical location in the universe. If you run computer simulations of structure formation in the universe, starting from the initial conditions revealed by the cosmic microwave background and evolving forward in time under the influence of gravity and dark matter, the typical velocity of galaxies like the Milky Way should be around 300 kilometers per second. Our measured velocity is about twice that. This discrepancy could mean that the large-scale structure in our region of the universe is more extreme than average. The Great Attractor and the Shapley supercluster might be more massive than typical structures, producing stronger gravitational pulls and higher velocities. Or it could mean that our simulations are missing something, some aspect of structure formation that we have not accounted for. Observations over the past few decades have revealed that bulk flows of galaxies extend to surprisingly large distances. A bulk flow is a coherent motion of a group of galaxies in the same direction, beyond what would be expected from random local gravitational interactions. Measurements of galaxy velocities using methods like the Tully-Fisher relation and the fundamental plane have shown that significant bulk flows extend to at least 200 to 300 million light-years, reaching velocities of 400 kilometers per second or more. These flows are larger and faster than standard models predict. Some studies suggest that the flows might extend even farther, implying that structure in the universe on scales of several hundred million light-years is more pronounced than we thought. If this is true, it could indicate that the initial conditions of the universe, as revealed by the cosmic microwave background, are not quite what we think. Or it could point to the influence of dark energy, the mysterious force causing the expansion of the universe to accelerate in ways we have not fully understood. The debate over bulk flows and their implications continues. Some measurements suggest large, coherent flows. Other measurements find smaller, less significant flows. The discrepancies might arise from differences in methodology, from biases in the samples of galaxies being studied, or from uncertainties in the distance measurements that are crucial for determining velocities. Measuring distances to galaxies is notoriously difficult. Astronomers use a cosmic distance ladder, a series of methods that build on each other, starting with nearby objects whose distances can be measured directly and extending to distant galaxies whose distances must be inferred indirectly. Each step in the ladder introduces uncertainties, and those uncertainties accumulate as you move to larger distances. Small errors in distance measurements can lead to large errors in inferred velocities, making it hard to determine whether observed motions are truly anomalous or just the result of measurement noise. This is where the nature of motion itself becomes philosophically intriguing. We have discussed the velocities at which you are moving through space, but what does it mean to say you are moving at 1.4 million miles per hour? Moving relative to what? The cosmic microwave background provides a convenient reference frame because it is nearly uniform across the sky, and its rest frame represents a kind of average over the entire observable universe. In the reference frame of the cosmic microwave background, the average velocity of galaxies is zero by definition. Any individual galaxy's velocity is measured relative to this average. But the cosmic microwave background rest frame is not special in any absolute sense. It is just a convenient choice, a reference frame that simplifies certain calculations and observations. From the perspective of someone in the Andromeda Galaxy, the Milky Way is moving in a different direction and at a different speed. From the perspective of someone in a distant galaxy billions of light years away, our motion might appear entirely different. There is no universal, absolute reference frame against which all motion can be measured. Motion is always relative. Einstein's theory of special relativity, published in 1905, formalized this idea with breathtaking mathematical precision. Special relativity states that the laws of physics are the same in all inertial reference frames, meaning reference frames moving at constant velocity relative to one another. There is no experiment you can perform to determine whether you are at rest or moving at constant velocity. The speed of light is the same in all inertial reference frames, regardless of the motion of the source or the observer. This constancy of the speed of light leads to counterintuitive consequences like time dilation and length contraction, where time passes at different rates and distances appear different depending on your state of motion. But these effects only become significant at speeds approaching the speed of light, about 300,000 kilometers per second. The cosmic velocities we have discussed, even the Milky Way's motion at 630 kilometers per second, are far below the speed of light. 630 kilometers per second is only about 0.2% of the speed of light. At such speeds, relativistic effects are negligible, and Newtonian mechanics provides an excellent approximation. General relativity, Einstein's theory of gravity, published in 1915, extends these ideas to include acceleration and curved spacetime. General relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Objects follow the straightest possible paths through this curved spacetime, which we perceive as motion under the influence of gravity. The Earth orbits the Sun not because the Sun exerts a force pulling the Earth toward it, but because the Sun's mass curves spacetime around it, and the Earth follows a curved path through that curved spacetime. This might seem like a subtle distinction, but it has profound implications. It means that falling under gravity is a form of inertial motion, indistinguishable from floating in empty space, far from any gravitating objects. An astronaut in orbit around the Earth is in free fall, accelerating toward the Earth at 9.8 meters per second squared due to gravity. But the astronaut feels no force. Inside the spacecraft, the astronaut floats weightlessly, because the spacecraft and everything inside it are falling together at the same rate. This is the equivalence principle, one of the foundational ideas of general relativity. Gravity and acceleration are locally indistinguishable. Here's where it gets strange. If you are in free fall, accelerating under gravity, you feel no force. But if you are standing on the surface of the Earth, resisting the pull of gravity, you feel a force. The ground pushes up on your feet, preventing you from falling. This upward force is what you perceive as weight. From the perspective of general relativity, standing still on the Earth's surface is not an inertial state. You are being accelerated upward by the ground at 9.8 meters per second squared, which exactly counteracts the curvature of spacetime that would otherwise cause you to fall. This is why you feel weight. It is not because gravity is pulling you down. It is because the ground is pushing you up, preventing you from following your natural inertial path through curved spacetime. This perspective flips the usual intuition about gravity. Falling is the natural, force-free state. Standing still requires a force. Apply this to cosmic motion. As the Milky Way falls toward the Great Attractor and the Shapley supercluster, it is following its natural inertial path through the curved spacetime shaped by the mass distribution of the universe. No force is required to maintain this motion. The Milky Way is simply following the curvature of space-time, just as the Earth follows the curvature of space-time around the Sun. This is why you feel nothing from the galaxy's motion. You are in free fall through the large-scale gravitational field of the universe. Everything around you is falling with you. There is no relative acceleration, no force, nothing for your senses to detect. The universe carries you along, and you drift through space-time on the path determined by the mass and energy around you. The expansion of space adds another layer to this picture. General relativity describes how space-time curves in response to mass and energy, but it also allows space-time itself to expand or contract. The expansion of the universe is a solution to Einstein's equations, discovered by Alexander Friedmann in 1922, and independently by Georges Lemaitre in 1927. Einstein initially resisted the idea of an expanding universe, even introducing a cosmological constant into his equations to produce a static universe. But after Hubble's observations in 1929 confirmed that distant galaxies are receding, Einstein abandoned the static model and accepted expansion. The expansion of space is not something that happens within space. It is the evolution of space itself. The distances between galaxies increase not because the galaxies are moving through space, but because the space between them is growing. This expansion does not affect bound systems like galaxies, galaxy clusters, or even small groups of galaxies like the local group. The gravitational binding in these systems is strong enough to resist the expansion. But on larger scales where matter is more diffusely distributed, expansion dominates. The rate of expansion is not uniform throughout the universe's history. In the early universe, expansion was slowing down due to the gravitational pull of matter. About 6 billion years ago, the expansion began accelerating, driven by dark energy, a mysterious form of energy that permeates all of space and exerts a repulsive effect on cosmological scales. Dark energy accounts for roughly 68% of the total energy density of the universe, far more than ordinary matter, which accounts for only about 5%. The remaining 27% is dark matter, which interacts gravitationally, but not electromagnetically, making it invisible to telescopes but detectable through its gravitational effects. The nature of dark energy is one of the biggest unsolved problems in physics. We know that it causes the expansion of the universe to accelerate, but we do not know what it is. It could be the energy of empty space itself, a vacuum energy that has a constant density everywhere and at all times. Or it could be a dynamic field, similar to the fields that produce other forces in nature, but with properties that cause it to have a repulsive gravitational effect. Distinguishing between these possibilities requires measuring the expansion rate of the universe at different times in its history, which astronomers do by observing distant supernovae, measuring the cosmic microwave background, and surveying the distribution of galaxies. These measurements have revealed that the accelerated expansion began relatively recently in cosmic history, about 6 billion years ago. Before that, the universe was decelerating. The transition from deceleration to acceleration marks a turning point in the universe's evolution. This acceleration has implications for the long-term future of our cosmic motion. As dark energy continues to drive the expansion, the rate of expansion will increase. Distant galaxy clusters that are currently receding from us will recede faster. Eventually, they will recede so fast that light from them will no longer be able to reach us. The observable universe will shrink, not because anything is moving into a black hole, but because the expansion of space will outpace the speed of light over large distances. Galaxies beyond a certain distance, called the cosmic event horizon, will disappear from view, their light stretched to infinite wavelengths by the expansion of space. This process will take trillions of years, but it is inevitable if dark energy remains constant. The Milky Way's motion toward the Great Attractor and the Shapley supercluster will eventually be overcome by the expansion of space, and those structures will recede from us, carried away by the accelerating expansion. But this will not happen for a very long time, far longer than the age of the universe so far. The measurements that reveal our cosmic motion rely on a variety of techniques, each with its own strengths and limitations. The motion of the Earth around the Sun is measured directly using observations of nearby stars, which appear to shift slightly in position over the course of a year due to parallax. This shift is tiny, less than 1 arc-second for even the nearest stars, but modern telescopes can measure it with exquisite precision. The Gaia satellite, launched by the European Space Agency in 2013, has measured the positions and motions of over 1 billion stars with unprecedented accuracy, creating a three-dimensional map of the Milky Way. These measurements confirm that the Earth orbits the Sun at 67,000 miles per hour and allow us to determine the Sun's motion through the galaxy with great precision. The Sun's orbital speed around the Milky Way is measured using several methods. One method involves observing the rotation curve of the galaxy, which plots the orbital speeds of stars and gas at different distances from the galactic center. The rotation curve reveals that stars far from the center are moving faster than expected based on the visible matter in the galaxy. This discrepancy is evidence for dark matter, an invisible form of matter that extends far beyond the visible disk of the galaxy. By measuring the rotation curve, astronomers can infer the total mass distribution of the galaxy, including dark matter, and determine the Sun's orbital speed. Another method involves measuring the proper motions of stars in the solar neighborhood. Stars near the Sun are also orbiting the galactic center, but at slightly different speeds depending on their distances from the center. By measuring the tiny shifts in the positions of these stars over time, astronomers can map out the velocity field in our region of the galaxy and determine the Sun's motion relative to the average motion of nearby stars. The Milky Way's motion through space is measured using the dipole in the cosmic microwave background. This measurement is remarkably precise because the cosmic microwave background is so uniform that even tiny deviations stand out clearly. The dipole amplitude is about 3 millikelvin out of a background temperature of 2.7 Kelvin, a fractional difference of about 1 part in 1,000. This dipole directly reveals the Milky Way's velocity relative to the cosmic microwave background rest frame. The direction of the dipole points toward the constellation Leo, indicating the direction of our motion. By subtracting the Earth's motion around the Sun, the Sun's motion around the galaxy, and the Milky Way's rotation, astronomers can isolate the motion of the local group relative to the cosmic microwave background. This motion is about 630 kilometers per second toward the constellation Hydra, driven by the gravitational pull of the Great Attractor and more distant structures. Measuring the masses and distances of structures like the Great Attractor and the Shapley supercluster is challenging because these structures are partially obscured by the disk of the Milky Way, a region astronomers call the zone of avoidance. Dust and stars in the galactic plane block our view of galaxies behind them, making it difficult to map the full extent of nearby structures. Astronomers overcome this using infrared and radio observations which can penetrate dust, and by observing the Doppler shifts of galaxies to infer their distances and motions even when direct imaging is difficult. The masses of these structures are inferred from their gravitational effects on surrounding galaxies. By measuring how fast galaxies are moving near the Great Attractor, astronomers can estimate the total mass required to produce those motions. The Shapley supercluster is estimated to contain roughly 10 quadrillion solar masses, making it one of the most massive structures within 1 billion light-years. Think about the precision required for these measurements. To detect the motion of the Milky Way through space, astronomers must measure temperature differences in the cosmic microwave background of less than 1 part in 1,000. To determine the Sun's orbital speed around the galaxy, they must track the positions of stars that are tens of thousands of light-years away and detect motion of a few milliarc seconds per year. To measure the expansion rate of the universe, they must observe supernovae billions of light-years away and determine their brightnesses and redshifts to a few % accuracy. Each of these measurements pushes the limits of current technology, requiring space-based telescopes, sensitive detectors, and sophisticated data analysis techniques. The fact that we can make these measurements at all, and that they agree with each other and with theoretical predictions, is a testament to the power of modern observational astronomy. But there are limits to what we can measure. The observable universe has a finite size, about 93 billion light-years in diameter, determined by the age of the universe and the speed of light. Light from objects beyond this distance has not had time to reach us yet, so we cannot observe them. This means we can only measure motion relative to structures within the observable universe. We cannot know whether the observable universe as a whole is moving relative to some larger structure beyond our view. Some cosmological theories suggest that our universe might be part of a multiverse, a vast collection of universes with different physical properties. If such a multiverse exists, the observable universe might be moving through it in ways we can never detect, because there is no way to observe anything beyond our cosmic horizon. This possibility is speculative, far beyond what current observations can test, but it highlights the fundamental limitation that we can only measure motion relative to other objects we can observe. Another intriguing question is whether our location in the universe is special or typical. The Copernican principle, named after Nicholas Copernicus, suggests that we do not occupy a privileged position. The Earth is not at the center of the solar system. The Sun is not at the center of the galaxy. The Milky Way is not at the center of the universe. By extension, the Copernican principle suggests that our location in space and time should be typical, not exceptional. If we observe something unusual, like a velocity that seems higher than average, the principle suggests that either our measurements are wrong, or the universe is structured in a way that makes such velocities more common than we thought. The alternative is to accept that we might be in an unusual location, a place where the large-scale structure happens to be more extreme than average. This possibility is uncomfortable because it seems to violate the Copernican principle, but it is not impossible. The universe is not perfectly uniform. Variations exist, and some regions will inevitably have more or less structure than the average. We might simply live in one of those regions. Surveys of large-scale structure over the past few decades have given us a better sense of how typical or atypical our location is. Projects like the Sloan Digital Sky Survey have mapped the positions and redshifts of millions of galaxies, creating three-dimensional maps of the universe out to distances of billions of light-years. These maps reveal a cosmic web of filaments, walls, and voids, with galaxies clustered along the filaments and around the nodes where filaments intersect. The Great Attractor and the Shapley supercluster are prominent features in this web, but they are not unique. Similar structures exist throughout the universe. Our high velocity relative to the cosmic microwave background is somewhat unusual, but not impossibly so. Simulations suggest that about 10 to 20% of galaxies should have velocities as high as ours or higher, depending on the details of structure formation in different regions. So while we might not be perfectly average, we are also not impossibly exceptional. Consider what this means for the experience of observers elsewhere in the universe. An alien astronomer in a galaxy within the Great Attractor would measure a different cosmic microwave background dipole, reflecting their galaxy's motion relative to the cosmic microwave background. An astronomer in a galaxy within a large void, far from any massive structures, might measure a much smaller velocity, because there would be fewer nearby structures pulling on their galaxy. An astronomer in a galaxy near the edge of the observable universe, as seen from Earth, would see a completely different set of nearby galaxies and structures, and their measurements of large-scale motion would reflect that different environment. Every observer in the universe has a unique perspective, shaped by their location and motion. But the laws of physics are the same everywhere, so every observer can apply the same principles to understand their motion and the structure around them. The long-term future of cosmic motion is intimately tied to the fate of the universe itself. If dark energy remains constant, as current observations suggest, the expansion of the universe will continue to accelerate forever. Distant structures will recede beyond the cosmic horizon, disappearing from view. Galaxies that are not gravitationally bound to our local group will become unreachable no matter how fast we could travel. The local group itself will likely merge into a single, massive galaxy over the next several trillion years, as the Milky Way, Andromeda, and smaller galaxies collide and coalesce. This merged galaxy will become increasingly isolated, surrounded by an expanding void as distant galaxies recede. Star formation will eventually cease as the supply of gas is exhausted. Existing stars will age and die, leaving behind white dwarfs, neutron stars, and black holes. Over timescales of 10 to the 100 years or more, even these remnants will decay or evaporate, leaving a cold, dark, diffuse soup of particles. If dark energy is not constant, the future could be different. If dark energy strengthens over time, the expansion could accelerate so rapidly that even bound systems like galaxies and eventually atoms themselves are torn apart. This scenario is called the Big Rip, and it would occur on a timescale of tens of billions of years if dark energy behaves in a particular way. If dark energy weakens over time, the expansion could slow and eventually reverse, leading to a big crunch where the universe collapses back on itself. Current observations do not favor either of these scenarios over the constant dark energy model, but the uncertainty in our understanding of dark energy leaves the door open to surprising possibilities. The fate of the universe depends on the properties of dark energy, which remain deeply mysterious. Return to the present moment, to you lying in your bed, motionless yet moving at over 1 million miles per hour. The layers of velocity we have explored are all real, all measurable, all consequences of the structure and evolution of the universe. You are part of a cosmic ballet that began 13.8 billion years ago with the Big Bang, and will continue for trillions of years into the future. The Earth's rotation carries you eastward at 1,000 miles per hour. The Earth's orbit carries you around the Sun at 67,000 miles per hour. The Sun's orbit carries you around the Milky Way at 500,000 miles per hour. The Milky Way's motion carries you toward the Great Attractor and the Shapley supercluster at over 1 million miles per hour. And beneath all of this, space itself expands, stretching the distances between unbound structures, reshaping the universe on the largest scales. The fact that you feel none of this motion is not a limitation of your senses. It is a fundamental consequence of the nature of motion itself. You cannot feel constant velocity, only changes in velocity. Everything in your immediate environment shares your motion, so there is no relative motion to detect. You are in free fall through the curved space-time of the universe, following your natural inertial path, and free fall produces no sensation of force. The illusion of stillness is perfect, because from your perspective, you are still. Motion is relative, and relative to everything around you, you are at rest. This realization connects to a deeper truth about the universe and our place in it. We are not separate from the cosmos, observing it from the outside. We are part of it, embedded in its structure, carried along by its motions, shaped by its forces. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. The Earth coalesced from the debris of those stellar deaths, a mote of dust that grew into a planet. Life arose on this planet, evolved over billions of years, and eventually produced beings capable of understanding their own cosmic motion. You are stardust, animated by the laws of physics, contemplating the universe that created you. The motion you cannot feel is the motion of the universe itself, the dance of matter and energy through space-time, the unfolding of a story that began with the Big Bang and continues into an unknown future. The velocities we have discussed are not abstract numbers. They are the result of forces and structures that have shaped the universe since the beginning of time. The rotation of the Earth is a remnant of the angular momentum present in the cloud of gas and dust that collapsed to form the solar system 4.6 billion years ago. The Earth's orbit around the Sun is determined by the balance between the Sun's gravity and the Earth's motion, a balance that has remained stable for billions of years. The Sun's orbit around the Milky Way traces the gravitational field of the galaxy, shaped by 200 billion stars and 10 times as much dark matter. The Milky Way's motion through space reflects the distribution of matter across hundreds of millions of light years, the gravitational legacy of density fluctuations that formed in the first moments after the Big Bang. Each layer of motion is a clue to the history and structure of the universe. By measuring these motions, astronomers can map the distribution of matter, test theories of gravity, constrain the properties of dark matter and dark energy, and probe the initial conditions of the universe. The cosmic microwave background dipole tells us about the gravitational pull of distant structures. The rotation curves of galaxies reveal the presence of dark matter. The expansion rate of the universe constrains the amount and properties of dark energy. Every measurement of motion is a piece of the puzzle, a glimpse into the workings of the cosmos. Here's the final mystery. Why is the universe structured the way it is? Why are there galaxies, clusters, superclusters, and voids? Why does the cosmic web have the particular pattern we observe? The answer traces back to the first moments after the Big Bang, when quantum fluctuations in the energy density of space were stretched to cosmic scales by a brief period of exponential expansion called inflation. These tiny fluctuations, with amplitudes of only 1 part in 100,000, served as the seeds for all the structure in the universe. Regions that were slightly denser than average attracted more matter, growing under their own gravity. Regions that were slightly less dense lost matter, becoming voids. Over billions of years, this process amplified the tiny initial fluctuations into the vast structures we see today. The cosmic microwave background provides a snapshot of these fluctuations as they existed 380,000 years after the Big Bang. By comparing the patterns in the cosmic microwave background to the distribution of galaxies today, astronomers can test theories of structure formation and constrain the properties of dark matter and dark energy. The connection between the earliest moments of the universe and our motion through space today is profound. The gravitational pull that drives the Milky Way toward the Great Attractor originated in quantum fluctuations that occurred a fraction of a second after the Big Bang. Those fluctuations were random, but they obeyed statistical rules that are imprinted in the cosmic microwave background and the large-scale structure of the universe. The fact that we can measure these patterns, connect them to theories of the early universe, and use them to predict the future evolution of cosmic structure is one of the great triumphs of modern cosmology. But mysteries remain. The nature of dark matter and dark energy are unknown. The origin of the initial fluctuations in the early universe is not fully understood. The ultimate fate of the universe depends on the behavior of dark energy, which we cannot predict with confidence. And we do not know whether our universe is typical among a larger multiverse of possible universes, or whether the conditions we observe are somehow special. These questions push at the boundaries of science, where observation meets theory and knowledge meets speculation. The journey from feeling nothing to understanding that you are moving at over 1 million miles per hour is a journey through layers of physics, history, and cosmic structure. It requires setting aside intuition, which tells you that motion should be felt, and embracing the counterintuitive reality that constant velocity is indistinguishable from rest. It requires understanding that motion is always relative, that there is no absolute reference frame, no privileged perspective from which the universe can be observed. It requires recognizing that gravity is not a force pulling you down, but the curvature of space-time, and that free fall is the natural, force-free state of motion. It requires appreciating the vastness of the universe, the timescales over which it evolves, and the intricate web of structure that has formed from the simplest of initial conditions. If these layers of cosmic motion fascinate you, consider the fact that future observations will continue to refine our understanding. New telescopes, both on the ground and in space, will map the large-scale structure of the universe with greater precision. Surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will observe billions of galaxies tracing the cosmic web in unprecedented detail. The Euclid satellite and the Nancy Grace Roman Space Telescope will measure the expansion history of the universe, constraining the properties of dark energy. Gravitational wave detectors like LIGO, Virgo, and the future space-based LASER will observe the mergers of black holes and neutron stars, probing the dynamics of gravity in extreme environments. Each of these projects will add new pieces to the puzzle, bringing us closer to understanding the full story of cosmic motion and structure. The silence of cosmic motion is one of the universe's great paradoxes. You move faster than sound, faster than a speeding bullet, faster than anything humans have ever built, yet the experience is one of perfect stillness. This paradox reveals something fundamental about the nature of reality. The universe does not care about human intuition. It operates according to laws that are often counterintuitive, but they are consistent, mathematical, and, with enough effort, comprehensible. The sensation of stillness you feel right now is an illusion, but it is an illusion grounded in the deepest principles of physics. It is an illusion that allows you to function, to think, to live, without being overwhelmed by the staggering velocities at which the universe carries you. Thanks for journeying through these layers of motion with me, from the spin of the Earth beneath your feet to the fall of the Milky Way toward distant gravitational beacons. If the idea that you're traveling at over 1 million miles per hour while feeling nothing resonates with you, there are more cosmic mysteries waiting to be explored in the videos below. Leave your thoughts in the comments about which layer of motion surprised you most. And until next time, rest easy, knowing that the universe carries you along on a path written in the geometry of space-time itself, a traveler through the cosmos, whether you feel it or not.